This presentation will introduce you to Tableau, which is data visualization software. You will also be examining the theoretical implications around visualizing data. Tableau Software is an American computer software company headquartered in Seattle, Washington. It produces a family of interactive data visualization products focused on business intelligence. The company was founded at Stanford University's Department of Computer Science between 1997 and 2002. Professor Pat Hanran and PhD student Chris Stolte, who specialized in visualization techniques for exploring and analyzing relational databases in data cubes, led research in the use of table-based displays to browse multidimensional relational databases. Together, they combined a structured query language for databases with a descriptive language for rendering graphics and invented a data visualization language known as VisQL, standing for Visual Query Language. VisQL formed the core of the Polaris system, an interface for exploring large, multidimensional databases. In 2003, after Stolte recruited his former business partner and friend Christian Chabot to serve as CEO of Tableau, it was spun out of Stanford with the software application. The product queries relational databases, cubes, cloud databases, and spreadsheets, and then generates a number of graph types that can be combined into dashboards and shared over computer networks or the internet. Tableau products include a variety of different applications, including Tableau Desktop, which is an application that allows you to drag and drop fields to analyze data, and users can then visualize the data and create dashboards. There's also Tableau Server, which offers a browser-based analytics application that anyone can use for business intelligence purposes. Tableau Online is a hosted version of the Tableau Server and allows users to share analytics and insights with anyone on the net. And then Tableau Public, it's a free version that allows users to use the basic functions of Tableau Desktop, but then also makes the analytics known to the public. And this is what we will be using in class. So why should we use Tableau? Well, first, it's easy to use. It does not require the use of any scripting language. It can also work with many different data sources. It can work with Microsoft Excel, with text files, databases, data marts, and etc. And it can connect directly to a data source. It's also quite fast. It can handle very large data sets efficiently. And its capabilities allow you to create interactive displays and easy to interpret graphs. However, there are some weaknesses of Tableau. First, it's not very comprehensive. It doesn't have data mining algorithms built in, so you are not able to do any predictive analytics. Also, it can't be integrated with other applications because the software is proprietary. It also does not include some visualization methods that are helpful. For instance, it does not include box plots, network graphs, tree maps, heat maps, or 3D scatter plots. However, when we look at why we should use data visualization in healthcare, it's due to the fact that charts have vast implications in research for potentially increasing interpretation efficiency while also limiting errors. The same would apply to healthcare. Most research and data visualization is theoretical and fails to establish the relationship between a graphical design and decision-making performance. It's hypothesized that charts may help overcome some of the human limitations with processing data that is stored in tables, which is a more traditional method for displaying results. That our early concepts were pioneered by Cleveland and McGill in the early 1980s, where they theorized about human graphical perception and how performance is time and task dependent. They demonstrated that the time of accurately extracting quantitative data from visual displays is dependent on the position, length, angle, and volume of the chart. When people make decisions in healthcare, they typically use a hypothetico-deductive model of acquiring and storing information. Let's consider a clinician's decision making. That is, a clinician will selectively acquire information in a logical fashion to make diagnoses and treatment decisions. As they acquire new information, they will refine their original hypothesis of a diagnosis or treatment. Unfortunately, this can result in problems because physicians may unintentionally distort the meaning of new information or even ignore findings so as to not contradict their original hypothesis. Also, the order in which the information is presented can result in an overemphasis or underemphasis of some of that data. So to overcome some of these limitations, research has explored concepts of graphical perception to develop methods of presenting quantitative and qualitative data in order to guide decision processes for diagnoses and treatments. In a way, charts may provide a way of presenting data by limiting cognitive processes involved in decision making. So in doing so, Cleveland and McGill summarized their findings by ranking various graphical techniques from the most to least accurate. This set the foundation for standardizing presentation methods for particularly quantitative data. Polister adapted Cleveland and McGill's principles and suggested that graphical reports of data can offer advantages over numerical reports by meeting requirements of human perceptions. Polister then developed guidelines to assist in the natural stages of perception in order to lessen the cognitive load of extracting information from charts. However, little research has actually explored whether such graphical techniques do in fact lead to decreases in the time it takes to interpret data and limit interpretation errors. Thus, we're actually going to look at some factors that can affect the interpretation of visual displays, including the context of the situation, the experience of the user, the type of chart, and the complexity of the data. In a study by Dixon, DeSanctis, and McBride, the researchers examined how the efficacy of charts to support decision-making is dependent on the task environment. They studied the role of task content, of the task complexity, and the task structure on the accuracy of interpreting financial data using bar and line charts versus tables, and using junior and senior level undergraduate business students. They discovered that charts were preferred with tasks that involve time dependency or of large amounts of data, and also when conveying a message from several sets of data on a common subject. Yet charts aren't always superior to tables. A study was conducted to determine how patients perceive various displays for determining the probability of treatment risks. So 6 different display methods, including the vertical bars shown on the left, the horizontal bars showed as the next over, followed by systemic ovals, then random ovals, then the pie charts, and numbers were used. And performance was measured in 2 different tasks. One required subjects to choose either a larger or smaller value, and another required participants to estimate a specific value. When the patients compared 2 sizes, the vertical bars resulted in the most accurate and fastest processing, followed by the systemic ovals. Now, for tasks that required greater precision, such as estimating the magnitude of a difference, the numbers were actually more accurate, followed by systemic ovals. Therefore, the researchers suggested that both vertical bars and numbers be used or only present the systemic ovals. It really depends on the context of the situation. When an expert makes decisions, such as a physician, they tend to make these decisions implicitly. What I mean is by that is saying that it's automatic. They don't necessarily have to burden themselves with processing many elements in order to make a decision. Thus, you would predict that more experienced people in a particular domain would make decisions in a non-reflective way when they are in a familiar situation. Thus, the presentation method should take into consideration the methods for experience of the users when using different graphical methods for making decisions. If performance cannot be enhanced further, it may not make sense to change a presentation method in more experienced professionals. So, what presentation method is best for the general population? Well, considering the ranking of presentation methods as described by Cleveland and McGill, one should always strive to choose a method that offers the greatest accuracy. So if we look at 5 lab tests, and we were compared between 3 groups, the dot plot offers, which shown on the right, offers an advantage because it only requires judgments regarding the position along a common scale, rather than judgments regarding position on identical but non-aligned scales as shown in the stacked bar plot on the left. Therefore, the stacked bar plot causes perceptual constraints that limit its interpretation. So let's look at some designs for presenting lab data. So Hoike and colleagues developed a method for displaying 3 or more lab results in a single display. The researchers transformed the entire range of lab results to fit within a range of 1 to 24. They utilized a background that consisted of colors to depict the departure of the parameters from their normal range. They used a plot that consists of a dot corresponding to each lab value with a line connecting each dot to form a polygon. The shape of the polygon could potentially indicate a disease. The plot you are viewing displays a patient with respiratory acidosis. It shows a value for pH, for the carbon dioxide, as well as for the actual bicarbonate. Unfortunately, if only 2 lab results were used, it forms a degenerate polygon. Also, the display requires relatively complex tasks in graphical perception by using judgment of position along identical non-aligned scales, and judgment of area and angle and color. Therefore, this display is very difficult to use. Hoagland offered some revisions to Hoke's display, which was shown previously. The major revision was to plot the complete set of data values on a vertical plane and inspect the degree of departure from normality by examining the deviations from linearity. Even though these modifications provide some improvements, it still includes judgment of angle and color. The greatest improvement was that rather than using judgment of position along non-aligned scales, you can actually compare results using judgment of position along a common scale. These were some of the earliest attempts at providing some practicality to Cleveland and McGill's theories. A more recent study by Bauer and colleagues examined speed and accuracy of interpreting frequently measured lab parameters in the pediatric intensive care unit and in the general ICU. They utilized spark lines, where the most proximate values are on the right leading edge of the line, and each historical data point is to the left on the tail of the spark line. When examining physicians of varying skill level, overall, the physicians were able to assess patients significantly faster with the graphical display compared to the tabular data shown on the bottom here, although there was considerable variation among physicians. The major findings were that the table shown below allowed physicians to identify values just outside the normal limits more accurately than the charts, yet the charts shown above were better at establishing trends and identifying fluctuating results. The complexity of the data should also be considered when designing a visual display. It can be very difficult to view multiple parameters on one display. It is recommended that if this is to be achieved, one would have to standardize the data to fit on some scale. Also, data transformation may have to be used if the data is not normally distributed in order to easily examine deviations from normal ranges. Finally, the display should be used to establish the relationship of the data you are viewing. For instance, viewing glucose and insulin levels in the same display may be helpful. There's been a lot of research in data visualization in the areas of genomics and proteomics, where a large number of data points are being examined simultaneously. Unfortunately, to the naive viewer, such displays appear confusing and busy. Therefore, there's a lot of work to be done in this area. So since I've been on this kick of presenting the topic of data visualization in the context of laboratory data and for physicians, I'd also like you to consider the point of designing something for multiple users. Laboratory data, for instance, is not just being presented to clinicians. Patients should also be able to view lab data and intuitively understand it. The fact is, we are moving towards a patient-centered healthcare system, where the patient is becoming an active participant in their healthcare decisions. Therefore, they should be able to interpret their medical information. A study was done that asked patients to judge the severity of risk factors for various diseases using charts and numbers. What the researchers found was that patients understood the charts better than the numbers alone. It's believed that this occurs because the charts limited the cognitive burden of the patients when interpreting the data. They did not need to process numerical information to be able to identify if something was high or low. They were able to make this decision explicitly by examining a chart. If patients could understand their health information, it's possible that this would motivate them to be an active participant in their healthcare. This could have far-reaching effects for chronic diseases like diabetes. For those of you that are interested in this topic, I really encourage you to look at the links on this slide to get more information. In particular, the TED Talk is a great speech by an editor for Wired magazine. I also provided the link for the accompanying article written by Wired magazine. Enjoy. It's an excellent TED Talk and article. That's a rapid video and rapid reading that I highly encourage you to read. But why use Tableau, and why is that preferred in healthcare? Well, this video actually offers a deeper understanding on how Tableau can be implemented and used in healthcare. Let's take a look.
Ultimately, we're all about patient care. We all work in this hospital because we want the best care for our patients and the best experience at what can be a really difficult time for them. And Tableau allows us to spend more time thinking directly about those things and less time on other things. St George's Hospital is a large teaching hospital in the south of London. We serve a population of well over 1 million. We have 8,000 plus staff. We're a large outfit. We cater for really major trauma cases all the way through to community services for Wandsworth. The benefit to presenting data visually as opposed to tables and numbers is quite profound in many ways. It's much easier for people to spot patterns when they're looking at data visually. I'd recommend Tableau to anyone, particularly healthcare professionals, because it allows us to understand our information and to inform decisions that we need to take quickly and effectively, which allows us to spend more time talking about things that really matter to the future of this hospital, in our case, and the future and care of our patients. A good example of life before and after Tableau would be the information we provide to our A&E department. So this is a very busy department. They need a lot of information about patients when they arrive, when they leave, did they need a bed, did they need a specialist opinion, all this sort of stuff. And before, we were drawing all that information together manually, lots of cutting and pasting around Excel, that sort of stuff, and it's just very laborious to produce the information. With Tableau, that process is streamlined, and the difference is before, given the time, we might not have that information ready till lunchtime, and now we're able to have that information ready 9 o'clock or so in the morning. As a patient at St George's, you wouldn't see Tableau directly, obviously, but you would receive the benefits of us using it. It would come in subtle forms. It would come in form of maybe slightly better organised facilities, slightly better decor even, better patient experience, maybe even better clinical outcomes, who knows. One of my favourite things about Tableau is when I get to use it to bust an anecdotally held truth or to disperse a myth that people think they understand about the service.
Let's also take a look at another video. This video offers a specific example of a way Tableau is being used currently with healthcare data. Let's take a look.
This is Sasha, and this 3-minute win is about some healthcare data. I've got some data loaded in here from a nationwide group of hospitals, and I'm going to start out by looking at how many days people stay in this hospital. And I want to split that up by clinical unit. Go ahead and sort that. And because length of stay days might differ from bed days, days are actually in a bed, I'm going to go ahead and put that on color. So I have a little bit of insight into that. And I want to be able to filter this by admit source. So I've got that over there. And I'll go ahead and rename this length of stay. And in a separate view, I want to look at how our number of new patients has changed over time. So I'm going to go ahead and look at some data there. I want to look at it by month, probably. I'll go ahead and put number of records on here, and I want to split that data up by gender, so I have some insight there. Okay, so now I can kind of look at how this trends over time, and I will call this timeline. And then lastly, I want to look at our different sites and what the average length of stay is by patient zip code. So I'm going to bring some of that information up on a map, and I'm going to put information about length of stay on size. This defaulted to some, but I actually want to be looking at the average length of stay. So I'm going to go ahead and change that. I only want to be looking here at the lower 48, so I'll change that. And maybe I want to make this a little bit prettier, add some transparency and a border. That looks good. So I'll call this my map, and then we'll go about building a dashboard. I'm going to put that length of stay information up top, and then put down here our timeline and our map. I want this to look good on a laptop. I want to make sure this applies to all the worksheets that reference this data source. And then I think I want this guy to be a filter, so that way we can drill down into all these different clinical units and what that looks like. But then I also would like for the map to be a filter so that I can drill down into different zip codes and understand what the behavior is there. I will call this clinical unit dashboard. Show the title, and there we go.
Another thing you are highly encouraged to read is the linked white paper, and this will allow you to get a better understanding on how software like Tableau can be leveraged for improving patient outcomes, which is incredibly important. Also, additional resources around Tableau can be found at the links listed on the screen. Again, visit these links to get more information on how Tableau is being used. As shown in this presentation, Tableau is software that can create rapid knowledge generation through data visualization. Specifically in healthcare, the use of such software has increased in popularity due to the influence on financials and patient outcomes. When using such software and creating a visual display of data, take into consideration the graphical method, the type of data, the experience of the user, and the complexity of the data.